The first review question wants you to find the area of the light shaded region. That's the region inside the 4-petal rose and inside the circle. Before watching the video, I would suggest you press pause and see if you can set up the integral that would find the area of the light shaded region. Press pause now. The item that is of most importance is the angle at which these two curves intersect. So if I draw the theta line here, I'm going to draw it as careful as I can. Okay, if I draw that theta line here, this becomes a very important theta. But before I find what that theta is, I would like you to see that this creates two very distinct areas. The first area goes from the origin out to the circle, and then origin out to the circle, making these small pie slices. Circle out to the circle, origin out to the circle, origin out to the circle, origin out to the circle, until we get to the theta line. Then once we get past the theta line, then we start going from the origin out to the rose curve. Origin out to the rose curve, origin out to the rose curve. Now my strategy is going to be to find the area of the red, then I'm going to add it to the area of blue, and then I'm going to take that and multiply it by 8, appealing to symmetry. Okay, now I've got to find this theta value. So this theta value is found by setting the curves equal to each other. 4 cosine 2 theta equals 2. So the cosine of 2 theta equals 1/2. And we know that's going to occur when 2 theta equals pi over 3, which means this is going to occur when theta equals pi over 6. Now in my strategy, which is not the only strategy, I need to find two other theta values. I need to find this theta value, which is clearly theta equals 0. And my other theta value is going to be when the rose comes back down to the origin. Now you may look at this, eyeball it, and say, alright, well that looks about halfway through, so you'd be guessing that theta equals pi over 4. Turns out you'd be guessing right. But let's take the guessing out of this and actually calculate when that rose comes back to the origin. So I will take my 4 cosine of 2 theta and set it equal to 0, and that's going to be when the cosine of 2 theta equals 0, and that's going to be when 2 theta equals pi over 2, so theta equals pi over 4, confirming what you might have already guessed. Now let's set up the integral to find the total area of the gray shaded region. So first I'll do the red region, which is going to be the integral from 0 to pi over 6 1/2 r, and r in this case is the radius of 2 squared d theta. Next I'm going to add the area of blue, and that will be the integral from pi over 6 to pi over 4 1/2 r, which is the function 4 cosine 2 theta, and that r gets squared, d theta. And finally I'll take the red plus blue, appealing to symmetry, and I'll multiply that entire thing by 8. That will give me the area of the gray shaded region. Perhaps when you attempted this, you looked at one of the petals and then multiplied by 4, in which case you would have something like this. For the red, we would take the integral from negative pi over 6 to positive pi over 6, 1/2 2 squared d theta. And then it is likely that you then did 2 times the integral from pi over 6 to pi over 4, taking the blue and multiplying it twice, 1/2 4 cosine 2 theta, quantity squared d theta, and then you would have taken this whole thing and multiplied it by 4. These are two ways you could have done it, but there are other ways. For example, you could have found the area of this entire pedal going from negative pi over 4 to positive pi over 4, and then you could have subtracted out this portion here, the dark shaded region. And again, applying or appealing to symmetry would have multiplied it by 4. So there are several ways. In all the ways, though, you definitely needed this theta equals pi over 6 and the theta equals pi over 4. And although the question did not call for it, you might want to check that you could do this on your calculator. You should get 9.827. The second item of review is to revisit homework number 47, where r squared equals 4 cosine of 2 theta. And it says find the area within one loop of this figure. We probably want to get a sense of what the shape looks like, and if you don't remember, you might have to put in the calculator. The problem is you have the square. So if you take the square root of both sides, then we should get plus or minus the square root of 4 cosine 2 theta. So I can enter this as two different r's, one r being the positive radical and the other r being the negative radical. And you can play with the window and the theta range a little bit to see what that looks like. Now, resolution may be an issue, so you're going to have some gaps and some funny looking things, but it should create this infinity looking shape, or the lemniscate. And we want to find the area within one loop of it. Like in the opening review problem, we're going to appeal to symmetry. I'm actually going to find just 1/2 of one loop, and then I'm going to multiply that area in yellow by 2 to get the answer that I desire. But before we do that, I want to investigate this problem because it's pretty neat. We have theta. Let me pick some theta values. 0, pi over 4, pi over 2, and let's look at the corresponding r values. So r at theta 0 is going to be 2. R at pi over 4 is going to be 0. So it looks like that's all that I need to get that yellow shaded region. But let's see what happens if I plug in pi over 2. If I plug pi over 2, since it's under the radical, we have a problem, and it's not going to exist. Does not exist. So it won't exist between or after pi over 4 all the way up to, let's say, 3 pi over 4. We have a gap or a range in which the function does not exist, and then it picks up again at 3 pi over 4, in which case r is 0, and then at pi r is going to be 2 again. So if I were actually tracing this, this part of the curve would be graphed first, and then there would be a gap because there's a whole bunch of values that don't exist, and then when it picks up again, it's actually going to trace this part of the curve. And it's going to keep repeating, and we can do something similar for the negative radical to get the rest of the curve. But the point I'm trying to make here is we can't just haphazardly integrate from 0 to 2 pi, because if we integrated from 0 to 2 pi, we'd be integrating over large ranges where the curve does not exist, and we're not able to do that. So this problem forces you to appeal to the symmetry. And the area then is going to be 2, because I'm taking the yellow and multiplying by 2 to get one loop, the area of one loop, and then my bounds are going to be from 0 to pi over 4, 1/2. Now I need to plug in r squared, but the good news is it's already put in terms of r squared, so then I will put 4 cosine 2 theta. I will not put the squared because it's already squared, d theta. Now I'd like you to solve this one by hand. So I'm going to ask you to press pause and do all of the operations by hand to come up with the area of one loop under this curve. Press pause now. When you come back, let's do this. So we have a bunch of things that are going to cancel out. The 2 cancels out with the 2, and I'm going to pull out the 4. Then I have the integral from 0 to pi over 4 of the cosine 2 theta d theta. Now please, let's not be silly here. You should be able to integrate this, which is going to be 1/2 sine 2 theta. So that's going to make 1/2 times the 4 is going to be a 2. Then it's going to be the sine of 2 theta, positive, and we're going from 0 to pi over 4. So this should work out real nicely. Now we have 2, the sine of 2 times pi over 4, which will give us pi over 2, minus the sine of 0, which itself is 0. So my answer is going to be 2 times 1, which is good old-fashioned number 2. In review problem number 3, we're going to look at homework number 48, a revisit. This is a very similar problem. Let's get a sense of what it looks like. So I'm going to say r equals positive radical 2 sine of 3 theta. And the other one, to make up the entire curve, would be negative radical 2 sine 3 theta. Now you'll graph this and play with it, and it won't look that great, but you should get a sense that this ends up looking like a 6-petal rose. And we're going to appeal to symmetry, and all we need is one of the 6 petals, and that one of the 6 petals is going to look like this. In your calculator, it actually looks like that, and it stops. It's a resolution issue, and it's not able to get the fine resolution to give you the entire petal. Let's look at a couple theta values. I'll go 0, pi over 6, pi over 3, and then the corresponding r's. So I'll have 0, radical 2, and 0 again. This is very similar because we're going to have another range where r does not exist before it picks up again at 2 pi over 3, which will give us 0, and then 5 pi over 6 gives us radical 2, and pi again gives us 0. We'll appeal to symmetry, find the area of one petal, and multiply it by 6. Our area then is going to be 6 times the integral from 0 to pi over 3. 1/2 r squared is already defined as r squared, 2 sine 3 theta d theta. Press pause and solve this one by hand too. And if you did it correctly, your answer should be the number 4. Review question number 4 will probably prove to be the most challenging. We have this curve r equals 3 cosine theta plus 2. Not 100% sure how to pronounce this. Limicon. Anyway, it has a big loop and then it has a little loop. And the question wants us to find the area inside the big loop but outside the little loop. So let's do some investigation. At theta equals 0, we're going to get the point here. Then as theta progresses, we'll move along this. Okay. And then at some point, we're going to touch back to the origin. Now, if I just integrated from theta 0 to that other theta, then I would find the area inside the large loop. I would find all of them. But that would prove to be too much because then I've filled in this little loop and I don't want the area inside the little loop. So I'm going to figure out, I'm going to continue with my theta progressing to get this part of the curve. I'll find the area of this blue and I'll subtract it from the area we found in red. I will take that result and multiply it by 2. That's my ultimate strategy. Let's start by finding where the red stops and the blue begins, which occurs at the origin. So that occurs when r equals 0. 3 cosine theta plus 2 will equal 0. 3 cosine theta equals negative 2. The cosine of theta equals negative 2/3. Well, to find that theta, we're going to have to express it as an inverse trig function. So theta is going to be the inverse cosine of negative 2/3, which is approximately 2.301. That's telling me less than pi. So I don't make a full complete pi revolution before the curve touches back to the origin. So interesting enough, as we go between 2.3 and pi, so theta equals here, we actually get negative r values. That's what sends this thing back inside the shape. So the red is created when theta is between 0 and the inverse cosine of negative 2/3, but then this blue portion is created when theta is between and some other value that brings us back to the point 10, and we have to compute that. It would be a mistake to let 3 cosine of theta plus 2 equal to 1, which it feels like it will. It feels like r should equal 1 at that point. Let's go ahead and solve this. The cosine of theta equals negative 1/3, and then theta equals the inverse cosine of negative 1/3. The problem with that value is less than 2.301, so that radius of 1 actually occurs out here somewhere. That value occurs out here somewhere. R equals 1 here. But I want this distance here. In fact, it's where r equals negative 1. So I could set 3 cosine theta plus 2 equal to negative 1, in which case we have 3 cosine of theta equals negative 3, or the cosine of theta equals negative 1. And that occurs at theta equals pi. We could also consider where the y coordinate equals 0. So y, we know, is going to equal r sine theta. So we could say, where does r, which is 3 cosine of theta plus 2 times the sine of theta, equal 0? In which case, by the zero product property, that would occur when theta equals 0, which is the first point we found way over here, and theta could equal, sneak this in, theta could equal pi, because the sine of pi is 0, and then this portion over here gives us what we found before when it touched at the origin, the inverse cosine of negative 2/3. Alright, let's fill this in. Let's erase this, and let's set up to find the required area. Area equals the integral from 0 to the inverse cosine of negative 2/3, 1/2 r squared. So that's my 3 cosine of theta plus 2 quantity squared d theta, and then I'm going to subtract the integral from the inverse cosine of negative 2/3 to pi 1/2 r squared d theta, and then I'm going to remember to multiply this entire thing, because that was the upper half red minus lower half blue. But if I then multiply this entire thing by 2, I will get the area that I desired.